Welcome! In this video I'll show you how to solve problem 4.5 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now this problem will allow us to further understand how to use spherical harmonics and also just get a better understanding of why they are actually the solutions to the angular part of the Schrödinger equation in 3D. Okay, so here what we want to do explicitly is we want to use these equations, right, our formulas that we have for the spherical harmonics to find the LL spherical harmonics, so when m is equal to L, and also for the specific case where L is equal to 3 and m is equal to 2. We want to then check that they satisfy the angular equation, which is what I wrote down here in red, and of course that is for appropriate values of L and m. So nothing too crazy. Let's begin by calculating the Lth angular spherical harmonic, so for YLL. Okay, so that's what we want to calculate first. So as I did, I think like 2 problems ago, in order for us to find this spherical harmonic, we begin by finding the Legendre polynomial. So let's see. Well, actually, we don't really need to do much. That's it. That's it. There's nothing more. There's a bar missing there. So actually, we don't really need to do anything new. That's literally all that there is, right? So this is our formula that we need, right? That's the Lth Legendre polynomial. And now we want to plug it into the formula for the associated Legendre polynomial, but this time L equal to m. So 1 minus x squared and L over 2. We don't need to worry about the absolute value because L is always positive. And now we need to take L derivatives. I need to take L derivatives of this thing right there, right? But this thing is simply a constant. It's a number, so we can put it to the front, maybe here, 1 over 2 to the L factorial. And then we also want to take L derivatives. So we are actually going to be taking 2 L derivatives, okay? And then we have x squared minus 1 to the L. Now notice that this thing right here, right, it's a polynomial. Each time you derive a polynomial, it goes down, it's the power of the polynomial, the order goes down by 1, right? So if it is x to the 5, it goes down to x to the 4. If it's x to the 4, it then goes down to x to the 3. Okay? So what we're going to have here after we multiply this through, it's going to be a polynomial of order 2L. Right? Because if L is equal to 3, for example, you would have x squared minus 1 cubed, and the highest value of x would be 6, right? And again, if L is equal to 3, that means you have to take 6 derivatives, which means that only the first element will survive, right? So every other number in this polynomial will eventually go to 0 after you take 2 L derivatives. Only the first one will not, right? So this derivative here, right, after you take 2 L derivatives, you only have this one, and what do you get? You get 2L factorial. Why? Because after one derivative, you multiply by 2L. After another derivative, you multiply by 2L minus 1. After the next one, 2L minus 2. After the next one, 2L minus 3, and so on, until eventually you get to all the way to 2L minus 2L, right? Like at the last one, it's 0 factorial. Actually, it's 1 before this. It should be 2L minus 1. But you get the point. It is, this thing right here will simply be 2L factorial. So this entire thing is simply 2L factorial inside the parentheses so that we don't think that we can simplify this, right? You cannot simplify this factorial with this one, right? It's like 6 factorial versus 3 factorial, for example. You can't just simplify this there. I mean, you can partially, but you still get all the elements that go between 2L and L. So there's not really all that much that we can simplify. Okay, so that is the associated Legendre polynomial. I think I can write this a little bit neater. I don't like the way this looks. So divided by 2 to the L factorial. There we go. That looks better. So now we need to plug this into our equation for the spherical harmonic. So YLL of theta comma phi. This is now this epsilon is -1 to the mth. So we get -1 to the L, square root of 2L plus 1 over 4 pi. And then we get L minus L factorial, this is still inside the square root, divided by 2L factorial. Okay, and then we have e to the IL phi, so e to the IL phi times this thing right there, except that this time instead of x we have cosine. So then we have the associated Legendre polynomial evaluated at cosine, yes, so we get 1 minus cosine squared of theta to the L over 2 the power, and then we have 2L factorial, and then we have 2L factorial. Okay, so let's see. -1 to the L will remain there. We have 2L plus 1. Let's keep it there for the moment. I don't think we can do much. 4 pi. L minus L factorial is 0 factorial, which is 1. So we get 1 over 2L factorial. Then we get this e to the IL phi. Now 1 minus cosine squared is sine. So we get sine squared to the L over 2, but the 1/2 factor will cancel out with the square, so we actually have sine of theta to the Lth power. And then we still have 2L factorial, which I guess we could write in here as 2L factorial squared, so 2L factorial squared, so that we end up simply with 2L factorial inside of the square root. And can we do something with this to the L? I don't think we can do much with it, right? So let's just put it here. So 2 to the L factorial. So there we go. That is YLL, right? So if ever you have you want to find the spherical harmonic for L equal M, then yeah, this is the formula to use. And we can also actually just factor a few things. So we have 1 over L factorial in front, then we have this square root. So just to write it a bit more compactly, and then we have minus 1/2 e to the I phi sine theta to the L. So that's just a bit more compactly written down, which I think is always nice. So now we want to go for the L equal 3, M equal 2, okay? So let's move to the side. Now, as before, we begin with the Legendre polynomial for L equals 3 in this case. So this would be 1 over 2 to the third power, which is 8, times 3 factorial. Now we need to take the third derivative. So that would be the third derivative. So this is dx 3 of x squared minus 1 cubed. All right. Now here, I think it is practical to just apply the chain rule here once. So apply one derivative. Let's see, 8 times 3 times 2. That's 24 times 2, that's 48, I believe. Now let's apply one derivative. So we still have 2. And we get 3x squared minus 1. And this is still squared times the derivative of what is inside, which is 2x. Now, we could just multiply this and then do 2 derivatives, or we can just do like chain rule. I don't know what would be easiest. I don't like having that many terms. So I think I'm just going to multiply first. So d squared dx squared. And this is 6x times x to the 4th minus 2x squared minus 1, plus 1, sorry. All right, so now let's just multiply through. So we would get 6x to the 5th minus 12x cubed plus 6x. So this is what we now need to take 2 derivatives of. So this would be 1 over 48. Now let's derive twice. So we get 6 times 5 times 4. 6 times 5 is 30, so that's 120 x cubed minus 12 times 3, which is 36, times 2, which is 72, x, and this goes to 0. All right, so we can do a little bit of simplifying here. So this would be, let's see, 4 I think is the easiest. Yeah, or 8. 8 could be faster. So 1 over 6 divided by 8, this would be 15 x cubed, and this is 9. So we can still simplify by 3 actually. So this would be 1/2 times 5x cubed minus 3x. Okay, so I think that's as simple as we can write it. Now let's go for the associated Legendre polynomial. So let me get rid of all of this just so that I can reuse this space. I mean, we already know what the polynomial is, so goodbye to all of that. So this is P3 of x. So now the associated Legendre polynomial, PLM, in this case 3, 2, this would be 1 minus x squared, and now m over 2, so 2 over 2, so 1. And then we have to take m derivatives, so that means 2 derivatives of what? Of this polynomial. So 1/2, which we can just put in front, and then 5x cubed minus 3x. So clearly, the 3x will not make it out of the derivative, but the 5x will. So 1 minus x squared. Now we take 2 derivatives, so we get 5 times 3 times 2, so that's 30x, and that's it. So now we simplify just a little bit more, so we get 15x times 1 minus x squared. Okay, so now that we have this, let's just plug it into our formula for the spherical harmonic. So let's do it perhaps somewhere over here. So this would be y32 of theta and phi. Let's see, so L is equal to 3, so we get 2 times 3, which is 6 plus 1, so 7 over 4 pi times L minus m, so 1 factorial, which is 1, and then we divide by 5 factorial, and then we have e to the 2i phi, and now we have our associated Legendre polynomial, which is 15, but not x, it is evaluated at cosine, so we get cosine theta 1 minus x squared, which is sine squared, so sine squared of theta. Okay, so is there anything we can simplify? There probably should be at least a little bit. I mean, we have 15 here and 5 here. So if we pull the 15 into our square root here, we have 15 squared. So 15 times 15. And down here, the 5 factorial is 5 times 4 times 3 times 2. So we could simplify this a little bit, right? 5 times 3 is 15. So this 15 goes away. And we still have 8, which I don't think we can do too much. So 8. So in the end, this would be 15 times 7. So that's 70. That's 105, I believe. So 105 divided by 32 pi. And then e to the 2i phi times, let's put the sign in first. I like having sign first. So there we go. That is the spherical harmonic for L equals 3 and M equals 2. So now comes the fun part. Now we want to see that the angular equation is indeed satisfied. So let me quickly clear some room. Okay, so let's begin with YLL. So to put this into our angular equation, let's first calculate a few things. For example, let's calculate the derivative of this spherical harmonic with respect to theta. So dyll d theta. So let's see. So all of these are constants that have nothing to do with theta, so no need to even touch them. So L factorial, square root of blah, blah, blah. None of this changes, blah, blah, blah. Okay, now we have this. So then we have minus 1 over 2 e to the I. I'm going to write it like this. So 2 to the L e to the I L phi, just because I want to make this as clear as possible. So we have sine of L theta. So we are taking the derivative of sine to the L of theta. So that would be, we have to apply the chain rule, L times sine of theta to the L minus 1 times now the derivative of what is inside, which would be cosine of theta. So that is what we get. That's the derivative. Then we need to multiply this by sine. So we multiply it by sine. So we multiply this by sine. So when we multiply this by sine, well, we get sine theta to the L again. So, this goes back to being L. Now we have to take another derivative with respect to theta. So now we take another derivative. Actually, let me do it like this. Sine theta, dy ll, d theta. Okay, and then we have all these things in front that, again, do not change. So square root 2l plus 1 factorial 4 pi. Then we have minus 1, 2 to the L, e to the I, L phi. And then we have, let's see, this L remains. Now we have to take the derivative of this. So let's do it step by step. First, we take the derivative of this. So we get, again, L sine of theta. This is now to the L minus 1. And we multiply by the derivative of what is inside, which is cosine. And then we derive by this, we multiply, by that. So we get cosine squared. Plus, now we leave the sine fixed, without doing anything. Sine theta to the L times cosine theta, its derivative. So we actually get minus, so we get minus sine. So we get a minus sign here, sine theta. Okay, so of course this is now L plus 1. Okay, that's pretty cool. And what else do we need to do? Now we need to multiply this again by sine of theta. So let's multiply this by sine of theta now. So times sine of theta. So by doing this, we get here sine theta to the L and here to the L plus 2. Okay, now what? So now we found this part. Okay, so what is this? What is it that we found? Notice that here we can factor out a few things. So let me rewrite this. So what we have here is 1 over L factorial square root of 2L plus 1 factorial over 4 pi. And then we have minus 1, 2 to the L, e to the I, L phi, that's a theta, phi. And notice that we can factor out sine theta to the L here. So we can just put it back in here, sine theta to the Lth power. And then we have L factor of L cosine squared minus sine squared. Okay? So, well, of course, this is cosine of theta and sine of theta. And what is this thing right there? Well, that's simply YLL. It's exactly YLL. So in the end, this entire thing is simply YLL times L cosine squared of theta minus sine squared of theta. So that is what we get there. Okay, then we have these two derivatives of our spherical harmonic with respect to phi. Okay, so let's see. The only place where phi appears is here. So that means that this will be a lot easier. So if we take two derivatives, we are basically taking the derivative of e to the I L phi, but 2 times. So we are going to get minus L squared e to the I L phi. So we get exactly the same thing as before, right? So this means that d squared y d phi squared, this is simply going to be minus L squared times y. Of course, this is for the case LL. Okay, so that's pretty simple. And then finally, we have this quantity right there. So I think that we are now in a position to put everything together. So let's see, this is what we know as the first part. So first we have YLL times L cosine squared of theta minus sine squared of theta. And then we have the second derivative with respect to phi. So we get minus L squared y, LL. And this has to be equal to, let's see, what is on the other side? This has to be equal to minus L plus 1. So this has to be equal to minus L plus 1 sine squared of theta times y, right? Let me just double check. I think that is it. Yes. Okay, so let's just take a moment to see what exactly we have here. So let's see, let's factor out all of our y's. So we have L squared cosine squared of theta minus L sine squared of theta minus L squared. All of this times, actually, let me put all to one side. So let's just do it plus L squared sine squared of theta, right? And then plus L sine squared of theta, and all of this times YLL. Okay, this has to be equal to 0. Now let's see, we have cosine squared sine squared. So of course we can factor out L squared cosine squared theta plus sine squared theta, which is 1. So bye-bye to this. And we also have minus L squared, this one. And then we have minus L sine squared and L sine squared, which cancel out. So, well, there we go. It is indeed equal to 0, right? 0 equals 0. So we can see that this is indeed a solution for this differential equation. Now let me clear the board and we will do the exact same thing, but for the other spherical harmonic. Okay, so now let's do the exact same procedure, but for this other spherical harmonic. So let's first calculate its derivative with respect to theta. So our constants, of course, will not change, 105, 32 pi, e to the 2I phi, and now we need to take this derivative. So we get 2 sine theta times the derivative of sine, which is cosine, so we get cosine squared of theta, plus, now we get sine squared, I'm using the product rule here, times the derivative of cosine theta, which is minus sine, so we get minus sine cubed. So this is what we get. Okay, now we need to multiply this by sine. So we multiply all of this by sine of theta. So we end up with sine squared here and sine to the 4th here. Okay, now we need to take another derivative. So let's take now the derivative with respect to theta of sine theta dy d theta. This is of course the case 3, 2. So again, these constants do not change. So this is 32 pi e to the 2I phi. And then we have, let's see. So again, we have to use product rule. This time there will also be a chain rule. So we get 4 times sine of theta. Now we need to multiply by the derivative of sine of theta. So we get cosine cubed of theta plus 4 sine squared of theta. I didn't touch it. Now the cosine theta times the derivative of cosine theta, which is minus sine. So minus, and we get sine cubed. And then we have this derivative, which will be minus 4 sine cubed of theta cosine theta. So actually these two add up, which is kind of nice. So these two are the same. So this will be minus 8. Okay, now we need to multiply this by sine, right? Considering this sine right there. So we multiply by sine and we get sine squared here and sine to the 4th power here. Okay, so what does this look like? Considering that we started with this, sine squared theta cosine theta, is there any way we could possibly simplify this? It doesn't really look like it at first glance. But notice that this first part is what we have right there, but times cosine theta. Look at this. This is very interesting. So we have 105 32 over pi e to the 2I phi. And by the way, why am I doing this? I'm doing this because that way I can rewrite this expression in terms of Y32, which would make the algebra much, much simpler like we did in the other case. So e to the I phi, and then we have sine squared of theta, cosine of theta, and now I just put everything that is extra, right? So 4 times cosine squared of theta. And then we do the same thing. So then we have minus 105 over 32 pi. I just multiplied through, that's what I did. And then e to the 2I phi, sine squared of theta, cosine of theta. And then I multiply by everything that is extra here, which is 8 sine squared of theta. So by doing this, we can see that this entire thing is simply y. So we get y32 4 times cosine squared of theta. And then we get minus 8 times y32 times sine squared of theta. So you can see that we considerably simplified how this looks. Now we go for the next part. So this derivative right there. Okay, so that derivative. Let's see, where's our expression? Maybe I'll go in this direction. So deriving by phi will be relatively easy here, right? So the only thing that has phi is e to the 2I phi. So if we want to take two derivatives, we simply get minus 4 times, well, that same thing, right? So y32. So we simply get a minus 4 in front. So that's, well, that's quite simple. That's quite simple. Okay. And finally here, well, there's not really too much to do except perhaps to calculate the product L plus 1. So the product here, if L is 3, would be minus 3 times 4. So that's minus 12. So minus 12 sine squared theta y. Okay, so let's now just plug everything into the angular equation. So we start up with this thing right there. So we start up with this. This is the first part. So this, and then we have plus the part corresponding to this right there, which is minus 4 y32. And this has to be equal to minus 12 sine squared of theta y32. So just like before, let's move everything to the left-hand side and see what we can do. So here we have 4. Now let's factor out the y's. So 4 cosine squared of theta minus 8 sine squared of theta minus 4 plus 12 sine squared of theta. And all of this is multiplied by y32 and is equal to 0. So here we have minus 8 plus 12. So this ends up being plus 4. So this and this is simply plus 4. Then we can factor out, we get 4 times sine squared of theta plus cosine squared of theta minus 4. So this is simply 1 here, and we end up quite clearly with 0. All right, so there we go. We just showed that both of those expressions are indeed solutions for the angular equation. So, you can just go ahead and use them accordingly. Just knock yourself out, have fun. So I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.